share this screen share, sir. Otherwise, we can minimize this one, sir. So we are live, sir. You can introduce yourself and start.
So how do you do screen share? From where?
Go here, sir. Click, sir. Here, sir.
Screen share. So when I write.
Yeah, when you want to write, sir. And then this button alone we should not never press.
Are we online now?
Yeah, we are online, sir. I'll just
so the questions appear here, huh?
Not here, sir. That another window is there, sir. YouTube. Here, sir. YouTube. Yes, sir. We are live, sir. Yes.
Okay, so students, good morning to all of you. If you have any questions, we can go about them right now, or else I have a few questions that we have seen from the online portal. And for example, there is a student Grish KH. The question asked is there excitation of electron from valence band to conduction band path dependent in any solar cell? So during process of electron moving from valence band to conduction band, is it free of interactions with photons? So the answer is that electrons get excited from valence to conduction band. They get then transported. Of course, they form exciton. This exciton gets broken into electron hole pair. And then these so exciton gets broken into free electron and free holes, which get transported to the respective electrode. So there is no as such interaction of electrons with the photons. Photon is a different entity, electron is a different entity. Photon is coming from light, which is what is giving rise to electrons and holes. So there is no interaction between photons and electrons. Okay. And the second question is by Jagdish Babu Bellam. He is the faculty. So the question is the depth of the subject is more for 8-week course. So in that sense, yes, I would agree with you. The course is a little bit involved and you need to be aware of fundamentals of semiconductors, fundamentals of light, interaction with matter, as well as fundamentals, as well as you need to read more about solar cell devices, and you need to be aware of p-n junction, you need to be aware of metal semiconductor contact. So there are some things which are assumed to be understood by the students. However, since each lecture is half an hour, you need to spend time reading, and unfortunately, without reading it's difficult to cope up with the course. So there is no substitute to reading. Lecture is one part of the learning and reading is another part of the learning, and both have to complement each other. So I'm sorry about that, but reading cannot be supplemented by anything else. Third comment is from T.S. Arundhati. When will the lecture materials be posted? So lecture materials will be posted, I think. Lecture videos are available. Materials, what do you mean by materials? The videos are available. We have given the references in the lectures, and notes. I think there are no notes. I mean, what you see on the video is the notes, and then you will have to read the books to supplement the notes. So reading of books is essential. So the course has various aspects to it. So for example, you need to read from any book on solar energy about fundamentals of solar energy. Then you need to read about semiconductors from any book on solid state physics and semiconductors, such as solid state physics by Kittel, or electronic properties of materials, Decker, or electronic and Magnetic Properties of Materials by R.E. Hummel. So there are a lot of books on semiconductors. Then PN junctions, again, you can read from PN junction diode, a book by George Newdeck, or you can also read about semiconductors from another book, Advanced Semiconductor Fundamentals by Robert Pierre. So there are a variety of books available. I have given the names of the books and all in the lectures as and when possible. So you need to get those books from some sources, not necessarily those books. These are some suggestive books. You can have different books. It's just the topic which is more important. So books are essential. You will have to get those books to get better understanding. And then we have Bhaskar. So NPTEL staff can tell you about when the lecture materials will be posted, but I think there is no PDF file here. It's just the video lectures which have to be posted, which are being posted to you, and they will be available on YouTube also later on. So unfortunately, there is no PDF file available here. You will have to read the books to supplement the lectures. And then we have Bhaskar Jyoti Das, whose question is again the similar. I'm having problems in finding book. So I cannot provide the PDF version. You will have to find the book yourself from your library or some other library in your city where you are. Or you can ask your library to buy the book for you. So the book has to be available to you. Or if you want, you can come to IIT Kanpur and you can send me a request on the email. We can photocopy the book and send it to you. At best, I can ask one of my staff to do that for you. And then can the professor share the slides? We are not using any slides as such. We are basically, most of the lectures are handwritten lectures. So what you see in the video is basically the slide. The videos can be paused also. So they will, you can make your own notes by looking at the videos. And then we have a question from Basavraj Huli. Please give numerical example on quantum efficiency and fill factor. Well, the fill factor is basically it determines how much is the maximum power that you can draw from a solar cell curve. So basically, the squarer or rectangle of the curve is, better the fill factor is. So ideally, the fill factor should be 100%. That means the maximum voltage and current that you should be able to draw should be equal to product of VOC and ISC. However, in real devices, the maximum voltage and maximum current that you can draw is always less than VOC and ISC. That is why it's called as a fill factor. So if I can give you a sort of a demonstration of it on my, so just 1 second. Let me just do the slide share.
Just a second. Yes.
So if I'm doing share. So fill factor is, so if this is the IV curve, so this is V, this is I, the rectangle that you can draw inside it corresponding to D of JV into V, dV is equal to 0. So this point is basically maximum power point at which this derivative is equal to 0. And so maximum possible voltage and current that is available as ISC into VOC. But what you get according to this is VM into IM. So let's say a numerical example is, so fill factor is essentially VM IM divided by VOC into ISC. So let's say we can also convert this into VM into JM divided by VOC into JSC. So let's say from a solar cell, JSC is equal to 20 milliamps per centimeter square, whereas JM is equal to, let's say, 15 milliamps per centimeter square, right? Similarly, let's say VOC is, let's say, 1 volt, and VM is 0.8 volt. So fill factor would be equal to 15 into 0.8 divided by 20 into 1, which is equal to 12 divided by 20. So you can say 60, you can say 0.6 or 60%. So basically, you are drawing only 60% of the theoretical power that can be available from a solar cell. So this is what is the meaning of solar cell. So you can say that maximum available to you is 20. You are drawing 15 from it. Okay. So basically, you can say this is watt per centimeter square. So you should be getting, ideally, you should be extracting 20 watts per centimeter square, milliwatts per centimeter square. And what you are extracting is basically 12 milliwatts per centimeter square. So I hope that is clear in terms of fill factor. Now, quantum efficiency, the second part is, so quantum efficiency is product of various quantum efficiencies, eta optical into eta absorption into eta exciton charge transport into eta charge collection and into eta exciton dissociation. So depending upon how much you lose at every point. So let's say, so this is eta EQE with respect to 100 photons, which are, so let's say you get 100 photons in there. So 100 photons are incident. Okay. So out of those 100, let's say I get, 5 reflected. So I will have 95 divided by 100 is the eta optical, which means 5 reflected. So I have lost 50. Okay. So efficiency is 95%. Now absorption. So let's say out of these remaining 95, so 95 now are left. And let's say I absorb all 95 of them. So I have optical efficiency, no loss in absorption. So this is 100%. This is 95%. Okay. Now, out of these 95 excitons, let's say, out of these 95 photons created, I create 95 excitons. And out of these 95 excitons, I am able to convert 90 of them into electron hole pair, free electron holes, and free electrons and holes. So let's say this is now 90 by 95. So this is the efficiency, 90 divided by 95, which I have for exciton dissociation. And if I calculate this number would be, let me just hang on, just calculate this. So it's 90 divided by 95. This is equal to 94.7. So you have 94% efficiency of exciton dissociation. So now you are left with 90 excitons. Now, out of those 90, how many reach the terminals? That is how many are transported. So let's say you lose 5 again. So let's say you have 85, you have 90 to begin with, and you lose, you receive 85 at the terminal. So which means 85 divided by 90 is the, so you can again calculate the efficiency, 85 divided by 90, which is 94% is the efficiency of, so 94 is the eta CT. And out of these 85, let's say you collect all of them. You don't recombine any of them at the contact. So this is 100% eta CC. So this is what is now, so you can now take a product of it, 0.95 into 1 into 0.947 into 0.94 into 1. So this will be the final quantum efficiency that will be there. So if you multiply all of this together, that is 0.95 into 1 into 0.947 into 0.94. This is equal to 84.5%. So you will get quantum efficiency of, so if you multiply this by 100, you will get quantum efficiency of 84.5%. This is what is meaning of quantum efficiency in the solar cell devices. And then another question is from, so I'll stop the screen share now. Okay. Another question is by Maideen. I think I can't read the full name correctly, but it's Jelani A, faculty. And though India has a lot of technology, why couldn't we manufacture for the solar panels? Well, we do manufacture solar panels. There are a lot of companies in India which are engaged in manufacturing solar panels, such as Adani Solar, Tata Solar, and Bikram Solar, and so on and so forth. However, India doesn't make silicon. The silicon is imported. So silicon wafer actually is imported from other places such as China. So yes, India does lack in manufacturing of silicon, but India does not lack in manufacturing of solar cell. India has good capability to manufacture solar cells. Then we have Sandeep Mohan Nayak. Please suggest how I design a bidirectional DC converter for grid connected PV system. Well, I mean, this course is not with DC converter, unfortunately, but if you want any help with DC converter, designing a grid connected PV system, you can send me an email. We can talk to you about that separately. This is not the objective of this course. So for that, we'll have to have a separate chat with each other. So you can send me an email. My email is available on the portal, and you can send me an email. Are there any other questions available?
Yes, sir. 3-4 questions came, sir.
So from which point onwards?
Sir, just scroll up, sir. Basvaraj Holi. Give one example.
Another question is by Basavraj Huli. Give one example on quantum efficiency and fill factor, which I have already given in numerical value. And another question is on please provide the notes. Well, I mean, there are no notes. You will have to look at the lectures, which are, and you can look at the lectures in slow motion as well. Can they look at the lectures in slow motion?
Yes, sir.
So you can look at the lectures in slow motion. So you can make your own notes from those. Kindly upload the PDF material. Well, there is no PDF material. There are only video lectures, and the book references are there. So you will have to get the books. I mean, we cannot help you with getting the books. You can write us, and to some of us, we can try and get the books photocopies posted, but that would not be possible for all the students. Or otherwise, if you want to come to IIT Kanpur, you are welcome, or any other IIT in your vicinity, any other good institution in your vicinity, you can visit, and I'm sure you can get the books from there. And a lot of these books are also available at low rates in stationery shops, bookshops. And then, well, I mean, somebody is asking about the quantum dots in solar cells. So I have not covered quantum dots in my course, but quantum dots basically are used as third generation solar cells, and they basically are expected to. The hope is that they will give rise to good solar cells, but right now the efficiency of these solar cells are around 10%, so they are not very efficient solar cells as of now. Nikhil is asking, please explain solar cell working once again. So, well, solar cell is nothing but a PN junction. So PN junction, when it is illuminated with light, suddenly the carriers it's flooded with the carriers, and as a result, you have at zero bias, you have holes, electrons flowing from P to N side and holes flowing from N to P side. And as you keep applying bias, you have the other diffusion current, minority diffusion current so electrons will go from N to P and holes will go from P to N. This current will oppose the photocurrent, and that will lead to reduction in the current as you sweep it. So basically, it's a diode working in the illumination of light, and sudden influx of carriers gives rise to current, which is generated by the solar cell. Your question is a little bit unclear as to what exactly you want to know, so I'm giving you a very general answer. If you have any specific question, you can write to me on email, which I can clarify. Somebody is again saying it is difficult to access all the books for us. This is an issue. I will talk to NPTEL office about it. A lot of people have raised this issue. However, I would suggest that if you have a good institute in your vicinity, such as an IIT or NIT or some university, you can get all the books from those places. And many of these books are also available on Amazon. You can buy these books from Amazon and Flipkart. And making an investment in books is always a good idea. So I would recommend you to buy these books. Some of these books are not available. They are available at low prices, and Amazon also sells used books at lower prices. So I would suggest that you buy these books, or otherwise you can visit institutions in your neighborhood, such as IITs and ITs, or state universities, or central universities, or even CSIR labs, and you can request them to make a photocopy of the book that is available there. So somebody will help you in those institutes. Certainly, if you want to visit, if you are in the vicinity of IIT Kanpur, you are welcome to visit IIT Kanpur, and we can help you in procuring the copies of these books. So what is somebody is asking why theoretical efficiency of solar cell is limited? Well, that is because of thermodynamic constraints. So thermodynamic constraints limit, so just like solar cell is also an engine in some sense. So just like an engine has a thermodynamic Carnot efficiency, for example, of an engine, similarly solar cells also have a thermodynamic efficiency limit, which is called a Schottky-Kaiser limit. And we didn't have time to go through that analysis because it would be a little too heavy for the course. But if you just Google about Schottky-Kaiser limit, and you will find this paper on Schottky-Kaiser limit analysis, which appeared long back in Journal of Applied Physics. So please go through that paper to see the derivation of the theoretical efficiency of solar cells. So can you provide the solution of numerical method related to sun and solar data has been discussed in week 1, formulas with full details? Well, I wish I could do that, but I think you need to be a little specific in your question. Your question is very general, Niharika. So I would request you to send me an email if you have any specific question instead of a general question, which unfortunately cannot be discussed right now. I mean, what kind of question you want, whether you want the questions related to time calculation, whether you want the question related to angle calculation, whether you want the question related to radiation calculation, you have to be more specific, and then we can talk about it. And then somebody is, Nikhil More is asking about what is the role of depletion region in solar cell. Well, depletion region will form in a solar cell because you have a PN junction. So whether you make a PN junction, whether you have a metal semiconductor junction, you will have a PN junction. Depending upon that, you will have a depletion region. So depletion region, in some sense, is basically a region in which no recombination takes place. It's a region with no charge carriers. As a result, the recombination depletion region is lower. So, however, in solar cells, this under illumination, we consider both generation and recombination under illumination. As a result, depletion region's role is to produce charge carriers as well as to lead to recombination. And we hope that the recombination current from depletion region is lower and generation current is higher, so that you have higher current overall in the solar cell. So basically, depletion region will be there if you have two different semiconductors. Because of band bending, you cannot avoid it. So depletion region can lead to both generation as well as recombination. The idea in a good solar cell is to maximize the generation current and minimize the recombination current. So
students are yet to pose their questions, sir. We will give them 5-10 minutes time.
That's okay.
Yes, sir. Otherwise, if they don't have many questions, we can conclude the session, sir. We will ask them to post.
So Neha Niharika is again asking, we do need the solution of numericals with full details. Please provide us. I would request you to type clearly, because many of you are using shorthand and some of it may not be very clear. So please type completely instead of typing in shorthand. Well, as I said, the solution of numericals you have to write to me. It is not possible to provide the complete solution of the numerical. This is just a live session to clarify certain doubts. Solution of numerical is an involved process, so you need to specify what kind of numericals, and you frame a particular problem, you post it, and then we will give you the solution. That is how it should work. Numerical solution is not possible on this portal as of now, because it's a more involved process, and we need to know what kind of numericals you are interested in. Okay. So as I said, you need to let me know whether you are interested in intensity calculation, whether you're interested in angle calculation, whether you're interested in time calculation, and it has to be again supplemented by some more information as to what exactly you want. So that is when we can help you with solution. But you can certainly email me and we will come back to you with a specific solution of a specific problem. So as far as books are concerned, you can follow the books that I have provided as references in the lectures, but you can also follow other books which I have not provided. So the bottom line is the book must have the content or the topic that I have discussed in the lecture. So there are basically 4 types of books. So let me just share the screen again. So if I go to, so basically books will be related to first solar energy related. So for example, in this, I will say solar energy by Sukhatme and Nayak. It is not a very expensive book. It is available on Amazon. You can buy it from there or Flipkart. Then we have, and then, or you can go to any library in the vicinity of you. And then we have another book on semiconductors that you will need. So any book will do, but I would suggest you can read Semiconductor Fundamentals. Volume 1 and Advanced Semiconductor Fundamentals, Volume 6 by Robert Pierre. But you can also look at electronic and magnetic properties of materials. R.E. Hummel. So this is also another good book. Then we come to PN Junction. In dark and in light. For this, I would suggest you read Physics of Solar Cells by Jenny Nelson. This is a very good book. So this will cover PN junction as well as solar PV technology. And then for certain technological issues, you will have to read review articles in journals. If you want specific review articles, for example, dye-sensitized solar cells, especially for dye-sensitized perovskite and organic solar cells, I would suggest you to go to Wikipedia and then go to journals and reviews. So there are a lot of reviews which are available. Some of them are open access as well, which can be accessed very easily by all of you. So these are a few books which I had recommended. The first one is on solar energy, Sukhatme and Nayak. That is for solar energy fundamentals. For semiconductors, I would say Semiconductor Fundamentals Volume 1 and Advanced Semiconductor Fundamentals Volume 6 by Robert Pierre. If you don't have this available, then Electronic and Magnetic Properties of Materials by Rolf Hummel, which is a very good book, and or any other book that can teach you semiconductor. So it's not necessarily these 2 books, any book that you can find available, that you can find in your vicinity. Then for PN junctions and solar cells, you can read Physics of Solar Cells by Jenny Nelson. Very good book, which explains, and by the way, this book also explains semiconductors. So you can also read generation recombination in this, generation and recombination in this book. And then we have technology related aspects, especially for DSSC, perovskite and organic solar cells, which are not possibly available in many books. As a result, it might be good to read them from review articles. However, I would recommend that you first go to Wikipedia, and Wikipedia has certain links for a few good papers that you can read to understand these technologies. So let me get back now. So let's stop again and then go back to live session. So what is the role of quantum physics in material science? Well, that's a very general question. Quantum physics is extremely important for a lot of devices. That's what I can say. So if you understand quantum mechanics, then that would be more clear. In fact, most of the semiconductor physics that we see is based on quantum mechanics. Then we have is temperature effect, any effect on efficiency of solar cell? Yes, temperature does have efficiency effect on solar cell. Efficiency of solar cell, generally, as you increase the temperature in the ambient, then solar cell efficiency goes down. And you can see if the sun is at 5800 Kelvin, your ambient temperature is 0 Kelvin, you will have certain efficiency. If you increase the temperature of ambient from 0 to 40, then of course your 0 degrees centigrade to 40 degrees centigrade, then obviously the efficiency will go down because of exchange of flux. So your exchange of flux will be lower, a little bit lower, not hell lot lower, but a little bit lower. Sir, tell me about quantum efficiency of solar cell. Well, quantum efficiency of solar cell is basically the efficiency by which, so we are talking about external quantum efficiency. So if you absorb, if 100 photons are incident to you on a solar cell surface, how many of them are eventually converted into electrons and holes that you have received that you have collected? So if you have 100 photons, potentially they can give you 100 electron hole pairs. If you collect all 100 of electrons and all 100 of holes, then you have 100% quantum efficiency. There is no loss. But if you lose, let's say 20 of them during reflection, during absorption, during transport, during exciton dissociation will come before charge transport. So reflection, absorption, exciton dissociation, charge transport, and charge collection. If you lose any photons on the way, then they will reduce the quantum efficiency. So suppose if you lose, I have explained this to some other student earlier. Can they go back to this again?
Yes, sir. It will be available, sir.
So this will be available to you. So if you scroll up the time in this video, you will see that I have explained what quantum efficiency means numerically. So somebody is asking about low-level injection. But low-level injection basically is in semiconductors that whatever perturbation you make, it doesn't affect the majority carrier concentration. It only affects the minority carrier concentration. So let's say if your majority carrier concentration in an N-type semiconductor, that is electrons, is 10 to the power 15 per centimeter cube, and your whole concentration is, let's say, 10 to the power 5 per centimeter cube, then if you make a perturbation of, let's say, 10 to the power 6 per centimeter cube by, let's say, light, then 10 to the power 6 is very small as compared to 10 to the power 15. So as a result, electron concentration virtually remains unaffected, but hole concentration is affected because it's comparable to the equilibrium hole concentration. As a result, minority carrier concentration is affected, but not the majority carrier concentration. This is what basically is a low-level injection.
Still, questions are yet to come, sir. We will request them to post, otherwise we can conclude, sir.
So can I just say?
Yeah, we can type or also orally also you can.
I think they don't have any questions.
Yeah.
So how are they able to listen to the voice?
Yeah, it's live only, sir. Right now we didn't put speaker, no, sir. Otherwise echo will come.
Where's the mic here?
Mic, webcam and mic is here, sir.
Okay.
So I'm just.
So how are they able to listen to the voice?
Sir, two more questions, sir.
Okay, so next question is, how can we differentiate PN junction diode and solar cell in its construction? Well, solar cell is a PN junction diode. It's just that PN junction diode normally is operated under dark, and PN junction, when you operate under light, it's a solar cell. Of course, with the appropriate band gaps and appropriate built-in field. The best material to make solar panel, well, I mean, right now silicon is the best material because it's most easily available and it's commercially the best in terms of lifetime and performance and cost. But there are other materials as well which are comparable, such as cadmium telluride and CIGS, copper indium gallium selenide. Third generation technologies are yet to make to the commercial market because there are certain issues with them. For example, Prof's kite has an issue with the lifetime, scalability, and presence of lead. Dye-sensitized solar cells have problem with lower efficiency as well as sealing problems because they use liquid dye, whereas organic solar cells have problem with lower efficiencies and scaling up as well as lifetimes. So right now, the best material is silicon. That is what is available commercially, and it's of low cost as well. The cost actually increases because of inverter and batteries in the domestic system. But if you have on-grid supply, then the cost is lowered. For example, right now, the tender that is floated for grid-connected electricity is about 2 rupees 50 paise, which is very low amount of money. So solar energy has become cheaper, a lot cheaper.
Can we conclude, sir?
Yeah, that's okay.
Yeah. Yes, sir.
So
we will end the session, sir.
We will end the session now. So somebody has asked question on solar panel. Can we make such solar panel like mobile screen fully transparent but work and for charge our mobile? Well, you can connect solar panel. Ideally, it's possible that you can have a solar cell connected to a mobile and which can charge it, just like you have in calculators. In calculators, if you see modern calculators, they have solar panel, little solar strip on top which charges the mobile battery, a calculator battery. However, in case of mobile phones, the power requirement is much more than the size of solar panel can give you on the mobile phone. So I mean, it's a possibility if you can make high efficiency solar cell, but we haven't seen too many examples as of now. Transparent solar cell, but if you make a transparent solar cell, then you're not going to absorb a lot of light into it, because most of the light that is absorbed is from the visible region. So if you don't absorb any light, then you're not going to convert a lot of that into electricity. So that remains an issue.
So Aman Lodha has asked throw some light on HET heterogeneity.
So HIT solar cells, basically, they are called as HIT because they are heterojunction, which is an intrinsic thin layer. So they were first launched by Sanyo, a company, and then used for their high efficient solar cells. Basically, it uses It uses an intrinsic region to absorb light. Two different semiconductor materials such as amorphous silicon, hydrogenated, and crystalline silicon are used in conjunction with each other to create a p-n junction. And it has a diffused heterojunction as an emitter. The region between p and n type material is an undoped region of intrinsic amorphous silicon layer. And this intrinsic amorphous silicon layer is a thin layer. So the total amorphous silicon, that is hydrogenated layer, is about 20 nanometer. And this 20 nanometer is a so if I draw the diagram of these two, so let me just go back here. So if I draw the diagram again, in the traditional solar cell, what we have is you have, let's say, P silicon, and then we have N silicon on top. This is about 600 nanometer. This is P plus on the back, about 10 micron. This is very thick, few hundred micron. So here we have back contact, and on top we have, and here we have a very thin layer of silicon nitride, which is anti-reflection coating, and then we have contacts. Okay, so these are front contacts buried into N silicon. This is the traditional design. In the HIT solar cell, what you have is, you have, this is N silicon. On the back, we have 20 nanometer amorphous silicon, that is hydrogenated. Then on the back, we have ITO electrode, which is 80 nanometer or so. And then we have back contact here. Okay. And so this is Shrokalski silicon. And then on top, we have a 15 nanometer P plus amorphous silicon. And so this is basically IP plus. Okay. And then we have 80 nanometer of ITO. And then we have front contact here. So this is what is a tradition. This will look like. So basically, you have amorphous silicon, crystalline silicon heterojunction, which is so amorphous silicon, crystalline silicon heterojunction gives you a band offset, and this is what is used for making a good solar cell. Amorphous silicon, the advantage is it passivates surface very well. As a result, it creates a good junction, and and it's also a low temperature sort of approach for making solar cells. So you have, this is what it is. So you have, if you look at the front, you have front contact, 18 nanometer ITO, followed by 15 nanometer of IP plus silicon. You have intrinsic P plus silicon, amorphous silicon. Then you have N silicon, which is single crystal. Then we have 20 nanometer of amorphous silicon, which is intrinsic again. So you can say this is IN plus. Okay. And then we have ITO. And then again, we have back contact. So these are contacts, metal contacts. So this is the difference between your, so you can see that this is, here you have a junction between P silicon and N silicon. Here you have also a junction, but it's a junction between crystalline silicon and amorphous silicon. So basically that is why it's called as heterojunction with intrinsic thin layer. It's a PN junction heterojunction with intrinsic silicon thin layer. And that is why it is called as HIT junction. Okay, so how much the um, how much the temperatures can solar cell withstand? Well, I mean, ideally solar cell can withstand, it depends upon the type of solar cell. I mean, silicon solar cell can withstand quite high temperatures, but at very high temperatures the contacts start having problems. They start having oxidation and wear and other kind of issues. So we don't operate solar cells beyond 40-50 degrees centigrade, or during daytime the temperature may reach about 70-80. But for example, for concentrated technology where the temperature can reach very high, you need to have cooling mechanisms to extract the heat. So very high temperatures lead to interdiffusion and reactions with the electrodes and degradation of electrodes. So you would not want to go beyond room temperature actually, which is, or the temperature, whatever temperature is available outside in the ambient, which is in the desert, it could be ambient temperature could be 45-50 in summer, but surface temperature could be about 80-90 degrees centigrade. So certainly not beyond that temperature, otherwise it will lead to degradation in the performance. Okay.
Yes, sir. We can post that message, sir.
So we will end the session now. If you have more questions, please ask them on the portal or by email. I'll be happy to answer them. So good luck with your lectures. Hope if you have any issues, you can always get back. But I hope it has been useful, and good luck with your exams. Thank you very much.
We'll stop the broadcast, sir.
Or you do that?
Just a second, sir.